Time is flying by on this busy, crowded planet. As life changes and evolves from second to second. At the same time, the arc of the human lifespan is getting longer. 67 years is the global average, up from just 20 years in the Stone Age. Modern science provides a humbling perspective. Our lives, indeed even that of the human species, are just a blip compared to the Earth, at 4.5 billion years and counting, and the universe at 13.7 billion years. It now appears the entire cosmos is living on borrowed time. It may be a blip within a much grander sweep of time. When, we now ask, will time end? Our lives are governed by cycles of waking and sleeping, the seasons, birth and death. Understanding time in cyclical terms connects us to the natural world, but it does not answer the questions of science. What explains Earth's past, its geological eras, and its ancient creatures? And where did our world come from? How and when will it end? In the revolutions spawned by Copernicus and Darwin, we began to see time as an arrow in a universe that's always changing. The 19th century physicist Ludwig Boltzmann found a law he believed governed the flight of time's arrow. Entropy, based on the second law of thermodynamics, holds that states of disorder tend to increase. From neat, orderly starting points, the elements, living things, the Earth, the Sun, the galaxy, are all headed eventually to states of high entropy or disorder. Nature fights this inevitable disintegration by constantly reassembling matter and energy into lower states of entropy, in cycles of death and rebirth. Will entropy someday win the battle and put the brakes on time's arrow? Or will time stubbornly keep moving forward? We are observers and pawns in this cosmic conflict. We seek mastery of time's workings, even as the clock ticks down to our own certain end. Our windows into the nature of time are the mechanisms we use to chart and measure a changing universe, from the mechanical clocks of old to the decay of radioactive elements, or telescopes that measure the speed of distant objects. Our lives move in sync with the 24-hour day, the time it takes the Earth to rotate once. Well, it's actually 23 hours, 56 minutes, and 4.1 seconds, if you're judging by the stars, not the sun. Earth got its spin at the time of its birth, from the bombardment of rocks and dust that formed it. But it's gradually losing it to drag from the moon's gravity. That's why, in the time of the dinosaurs, a year was 370 days, and why we have to add a leap second to our clocks about every 18 months. In a few 100 million years, we'll gain a whole hour. The day-night cycle is so reliable that it has come to regulate our internal chemistry. The fading rays of the sun, picked up by our retinas, set our so-called circadian rhythms in motion. That's when our brains begin to secrete melatonin, a hormone that tells our bodies to get ready for sleep. Finally, in the light of morning, the flow of melatonin stops. Our blood pressure spikes. Body temperature and heart rate rise as we move out into the world. Our days and our lives are short in cosmic terms. But with our minds, we have learned to follow time's trail out to longer and longer intervals. We know from precise measurements that the Earth goes around the Sun every 365.256366 days. Much of the solar energy that hits our planet is reflected back to space or absorbed by dust and clouds. The rest sets our planet in motion. You can see it in the annual melting and refreezing of ice at the poles, in the ebb and flow of heat in the tropical oceans, or seasonal cycles of chlorophyll production in plants on land and at sea. These cycles are embedded in still longer Earth cycles. Ocean currents, for example, are thought to make complete cycles ranging from 4 to around 16 centuries. Moving out in time, as the Earth rotates on its axis, it makes a series of interlocking wobbles called Milankovitch cycles. They have been blamed for the onset of ice ages about every 100,000 years. Then there's the carbon cycle. Plants capture it from the air or the sea. It finds its way into soils or ocean sediments as plants decay or as waste passes out of the food chain. It can take a volcanic explosion or a dramatic lowering of sea levels to release this carbon back into the air, often after millions of years. The processes that shape a planet like ours play only the smallest of roles in the evolution of the universe. So to glimpse time's broader arcs, we must look to cycles that govern the larger cosmos. The reigning theory is that the universe began in a sudden expansion of space, the Big Bang. With entropy uniformly low, this was the time of the tiny. Subatomic particles like quarks and leptons stirred into a hot soup. They combined into atoms, setting in motion the primordial era. The universe cooled as it ballooned, growing dim and falling into what's known as the cosmic dark ages. After several 100 million years, larger clumps of matter had drawn together. These isolated pockets of gas became dense enough to heat up and ignite. So began the era of stars. In this glorious age, the universe seeded the rich cosmic landscapes we see in our telescopes. Trillions upon trillions of stars lit up galaxies all across the cosmos. The arc of this era is defined by the life cycles of stars, which vary according to their sizes. Stars shine because gravity crushes matter into their cores. The energy released pushes outward and balances the inward force of gravity. This battle between energy and gravity is raging in stars all around the universe. But in large stars, about 10 million years after their birth, gravity begins to gain the edge. When the mass concentrating in the core of the star reaches a critical threshold, the core collapses in on itself. The energy released in the collapse causes the star to explode in a blast of light and debris that's visible across the cosmos. In the wake of this supernova, shock waves can cause nearby clouds of dust and gas to collapse and ignite to form generations of smaller stars like our Sun. A byproduct of star formation, solar systems form in the collapse of the surrounding solar nebula. The life cycle of planets, especially those in close, is tied to that of their parent stars. As stars like our Sun age, they grow hotter and more luminous. Billions of years from now, that will spell the beginning of the end for our home planet. As raging solar winds begin to blast away at our atmosphere, surface water will gradually disappear, rendering Earth uninhabitable. Finally, the Sun will begin to swell, growing so large that it actually envelops the Earth. Friction with the Sun's outer edges will cause this once blue world to gradually spiral inward. Unless they are large enough to go supernova, most stars end their lives in more of a whimper than a bang, as shown in this gallery of dying stars captured by the Hubble Space Telescope. In time, solar winds push their outer layers so far out, they blossom in spectacular displays. That's just what happened about 12,000 years ago to the star that spawned the famed Helix Nebula. On the inside, spokes of denser gas stubbornly resist the star's relentless winds. The star itself is now a dim, cooling remnant called a white dwarf. It's the size of Earth, but about 200,000 times more dense. This is likely what's in store for our Sun. A distant civilization may scan it for planets, but by then they won't see Earth. This battle between energy and gravity repeats in every corner of a galaxy like ours, with gravity drawing gas clouds into stars, and stars burning themselves out on a variety of timescales. In time, though, as the mass of the galaxy collects in successive generations of small stars, it will grow dimmer and dimmer. Some galaxies will see a temporary rebirth if their mass gets stirred up and combined with another. That's what's destined to happen to our Milky Way. At just about the time our Sun begins to swallow our planet, any remaining Earthlings will see the stars of the Andromeda Galaxy looming above the plane of our Milky Way. As shown in this simulation, the two are likely to tear each other apart. If it's a direct hit, the stars in both galaxies will gradually join together in a gigantic galactic puffball known as an elliptical galaxy. All the turbulence of the merger could stimulate a wave of new stars being born, reinvigorating the new, larger galaxy. Dust-ups like this, in which galactic neighbors merge, will be common as the era of stars moves into its later stages. But a wholesale thinning out of the universe is inevitable. On a grand scale, recent studies of the cosmic expansion rate show that the universe as a whole is in no danger of succumbing to gravity or of ending in a big crunch. In fact, over the last 6 billion years, the universe has begun to accelerate outward. Gravity is losing its grip to an unseen force called dark energy. You can see evidence of this now, out in the huge voids of space between filaments of galaxies. These voids are like ever-expanding bubbles. Where the bubble walls touch, you can see filaments of galaxies. As the bubbles grow, the filaments will stretch and break. The distance between galaxies will widen at a faster and faster pace. Eventually, no matter where you are in the universe, you will see only a few isolated clusters of galaxies huddled together, with little connection to anything else, and few clues to how they got there. At more distant reaches of time, tens of billions of years from now, the sky will grow darker and darker as everything recedes away from everything else. A good place to be in those long twilight years of the stellar era is a place where gravity and energy have forged an extended truce. Perhaps a place like this. Not much larger than our planet Jupiter, a red dwarf is one of the smallest and dimmest stars in our universe. They have been shown to harbor planets close enough that their dim rays can sustain liquid water and life. Brown dwarfs and red dwarfs form the vast majority of stars in our galaxy. In fact, combined, their mass exceeds that of all the large stars. Because they burn so slowly, they'll be the final beacons of the majestic age of stars, an era that will extend out to 100 trillion years. Even as their host galaxies grow dim, another process will begin to transform these small outposts. Over time, chance encounters between objects will perturb their orbits, sending some toward the center of the galaxy and others out into the void. In this way, galaxies may gradually evaporate, with ever denser concentrations of matter accumulating in their cores. As that happens, the universe begins to take on a new character. Welcome to the degenerate era, in which the universe is populated by red and white dwarf stars steadily cooling, and by the charred remains of supernova explosions, neutron stars. Even though these dead stars have used up their nuclear fuels, they continue to produce small amounts of energy. They scoop up and annihilate dark matter particles that manage to stray into their grasp. Here is where cosmic evolution slows to a crawl. It's expected that protons, the building blocks of all atoms, will slowly degrade, turning into subatomic particles that then decay into photons. All the protons in existence date back to the early moments of the universe. Their eventual decay will mark the end of the degenerate era. Around a billion years after the Big Bang. That's a 1 followed by 40 zeros. Our picture of what happens after that depends on what we learn in the coming years beneath the border of France and Switzerland, in one of the largest physics experiments ever undertaken. 100 meters underground, the Large Hadron Collider was built to accelerate particles in opposite directions through a giant ring 27 kilometers around. When they reach nearly the speed of light, scientists will bring them into ferocious collisions. One goal: to define the final time horizons of our universe, as well as the final moments of its most persistent objects. Black holes, ranging from millions to tens of billions of times the mass of our Sun, occupy the centers of large galaxies today. As those galaxies age, over trillions of years of time, much of their mass will spiral toward the center and into the jaws of ever more ravenous black holes. Conceivably, these black holes could end up weighing as much as a galaxy. But when they finally stop growing, will they too be subject to the ravages of time? According to the physicist Stephen Hawking, the answer is yes. He proposed a theoretical process of decay that scientists are hoping to test in high-energy particle collisions at the Large Hadron Collider. The idea is that throughout our universe, particles of opposite charge constantly well up in the vacuum of space. They normally destroy each other. But when this happens at the event horizon of a black hole, one particle can be pulled in while the other escapes. That has the effect of slowly siphoning energy and mass from the whole. If this is true, then even black holes are eventually doomed. But finding out for sure is not easy. Creating a micro-black hole, it seems, will take more energy than any Earth-bound collider can pack. That is, unless there's more to nature and to gravity than we've thought. The key lies in whether the universe we know is part of a more complex cosmic reality beyond the three spatial dimensions, plus time, that we experience in our everyday lives. We may be like an insect living on the two-dimensional surface of a pond, unaware of the deep and complex reality below it. It may be possible that an unseen extra dimension could intersect our world on an extremely tiny scale. According to some scientists, when particles collide at very high energies, the additional gravity needed to create a micro-black hole could come from the extra dimension. They'll know a black hole is there when they see the shower of particles predicted by Hawking's theory. Its presence will open a brief window to a deeper cosmic reality, while shedding light on the ultimate future of our universe. Based on Hawking's theory, a black hole observed today will take its last gasp when the clock strikes 10 to the 100th years from now, a number known as a googol. That's the end of the universe as we know it. But look beyond that to say 10 to the googol, a googolplex years. If you wrote all the zeros in that number in tiny one-point font, it would stretch beyond the observable universe. Will the great arrow of time have come to rest by then? Not if modern theories are correct. They hold that our universe is part of a much larger cosmic cycle of birth and death, with whole new universes coming into being in the space beyond our own. The time horizons of our universe may well be a blip in this grander scheme of things. Back to Earth now. We are products of the great era of stars and witnesses to its great spectacles of gravity and energy. No doubt there are other beings somewhere out there who are attempting to comprehend the universe. They too may invent the idea of time and develop their own theories on where it's all leading. Their discoveries and ours will not survive the entropy at work in the universe, as we all go the way of the stars, and as our universe gives way to grand new eras in the life of the cosmos. It may be a blip within a much grander sweep of time. When, we now ask, will time end? Our lives are governed by cycles of waking and sleeping, the seasons, birth and death. Understanding time in cyclical terms connects us to the natural world, but it does not answer the questions of science. What explains Earth's past, its geological eras and its ancient creatures? And where did our world come from? How and when will it end objects? Our lives move in sync with the 24-hour day, the time it takes the Earth to rotate once. Well, it's actually 23 hours, 56 minutes, and 4.1 seconds, if you're judging by the stars, not the sun. Earth got its spin at the time of its birth, from the bombardment of rocks and dust that formed it. But it's gradually losing it to drag from the moon's gravity. That's why, in the time of the dinosaurs, a year was 370 days, and why we have to add a leap second to our clocks about every 18 months. In a few 100 million years. In the revolutions spawned by Copernicus and Darwin, we began to see time as an arrow in a universe that's always changing. The 19th century physicist Ludwig Boltzmann found a law he believed governed the flight of time's arrow. Entropy, based on the second law of thermodynamics, holds that states of disorder tend to increase. From neat, orderly starting points, the elements, living things, the Earth, the Sun, the galaxy, are all headed eventually to states of high entropy or disorder. Nature fights this inevitable disintegration by constantly reassembling matter and energy into lower states of entropy, in cycles of death and rebirth. Will entropy someday win the battle and put the brakes on time's arrow? Or will time stubbornly keep moving forward? We are observers and pawns in this cosmic conflict. We seek mastery of time's workings, even as the clock ticks down to our own certain end. Our windows into the nature of time are the mechanisms we use to chart and measure a changing universe, from the mechanical clocks of old to the decay of radioactive elements, or telescopes that measure the speed of distance. Time is flying by on this busy, crowded planet. As life changes and evolves from second to second. At the same time, the arc of the human lifespan is getting longer. 67 years is the global average, up from just 20 years in the Stone Age. Modern science provides a humbling perspective. Our lives, indeed even that of the human species, are just a blip compared to the Earth, at 4.5 billion years and counting, and the universe at 13.7 billion years. It now appears the entire cosmos is living on borrowed time.